Okay, Newton's method. We're going to just do a quick overview of Newton's method. Basically, the quadratic formula has been known for a long time. And then there was a cubic and a fourth power quartic equation formula developed, but they are very complicated, therefore they're not very user-friendly. Now, once you get above a fourth power, there are no formulas that can be used to get exact answers. So we need some way to be able to try to approximate our answers for where our functions are crossing the axes. Well, basically it boils down to looking at our equation of a line, and here we're looking at our point slope formula. And we have our slope, which you know your slope is really just your derivative, and then you have your point. So we have our point slope formula, but instead of having an m here, we have our derivative. So Newton's method says, well, I'm going to go ahead and use this idea of a point. And I'm going to figure out the tangent line at this point. Well, we would be using our derivative to get our slope. We'd have our x-coordinate. We'd have our y-coordinate. And then we know it's pretty easy to figure out y, or when your line crosses the x-axis, and that's when your y is 0. Now, we are interested in the x, so all we want to do is go ahead and basically solve it for this x. When you get x on one side by itself, you end up with Newton's formula down here. Basically, you're choosing an x value, figuring out the equation of your tangent line, finding the 0. Once we have that, we're going ahead and repeating that. We're going ahead and finding the equation of the tangent line to that one, and we're finding the 0 for that one, and you're repeating that process over and over. And as you do that, you start getting closer and closer to where your function's crossing your x-axis. Typically, if you repeat that process, this iterative process, 3 times, you can probably get 4 to 5 decimal places of accuracy. You maybe do it 4 times, you probably have at least 6 decimal places of accuracy, which for most practical purposes is more accuracy than you really need. So Newton's method is not overly complicated, but it's not as easy as going 2 plus 2, but it's not far from that. So now let's go ahead and take a look at differentials. Once again, we're for the most part going ahead and we're looking at the equation of our lines. So we have our point slope formula here, where we have our x coordinate of our point, our y coordinate of our point, and then what this is really just your slope. Now, all we're going to do is try to get y by itself, because typically we would like y by itself, so we're going to add an f of a to both sides. And that's how we come up with the equation of a line that's tangent to a curve. For the most part, when you're looking at your graph over here, when you're looking at points close to x being a, there's not really much difference between your function and your tangent line. So we can really approximate anything on this curve in the neighborhood of a by just using your tangent line. And so that's what we are calling our linear approximation. Is it an exact representation? No, but it's a linear approximation of everything near or in the neighborhood of a. So let's go ahead and look at our function. and use our linear approximation formula to find the line that we can use to approximate our curve. So we're going to go L of x, f of a, and in this case a is 0, plus f prime of a, and a is 0, minus x minus, or in parentheses, x minus a, which is 0. Well, you need to go ahead and figure out what f of 0 is here. So you plug 0 into your function. You get the square root of 1, or 1. You also need to go ahead and figure out your derivative so you can do the green part. So you take your derivative of what we have over there, put your exponent in front, decrease your exponent by 1 times the derivative of the inside, so you're multiplying by 1. Then you got to actually go ahead and plug in 0 to that derivative. So then you get on the bottom the square root of 1, which is 1, doesn't change it, so it's just a half. Well, we're going to replace this with a 1. Replace this with what we figured out of being a half. And then our x minus 0 is just an x. So this is our linear approximation, which would allow us to be able to approximate what this function is when we are in the neighborhood of a. This function here is for the most part easier to work with than this one up here. If I wanted to do an approximation when x was, say, a half, I would get 1 plus a half times a half, or 1 plus a fourth, so I get 1 and a fourth, or 1.25. If I plug in a half up here, I get the square root of 3 halves, which would be the square root of 3 over the square root of 2. Rationalize that, I get the square root of 6 over the square root of 2. I don't really know that approximation off the top of my head. By the way, if you did do that approximation, it would be close to what we had down here, 1 1/4. So we're now going to take a look at trying to use our linear approximation to approximate this one here. You might say there is no function. Well, your function is really just taking something you're putting in and raising it to the 2/3 power. Now, raising it to the 2/3 power means you got to take the cube root. What number is close to this that's easy to take the cube root of? So that's 125, because you know the cube root of 125 is 5. So we're going to use a being 125. So we're going to go ahead and use our linear approximation formula. So we'll go f of 125. So you put 125 in here, take your cube root. It's 5 squared, so you get 25. Then you got to go ahead and plug your 125 into your derivative. So you got to go ahead and find your derivative. And then you got to go x minus 125. So to find your derivative, put your 2/3 in front, decrease your exponent by 1. Plug in 125 into your derivative, 2/3. Plug a 125 in here, it'd be a 5, but it's a negative exponent, so it puts it in the bottom. So it'd be a 5 times your 3 in the bottom. So 2/15. We now want to actually approximate what 122 is. So we're going to plug in 122 into our linear approximator. So we'll go 25, 2/15, 122 minus 125. Well, we know that's just a -3. -3 times that. So we get 25 plus a -2/5, which is 24.6. If you'd actually do the approximation of this on your calculator, remembering you put your whole exponent in parentheses, you would get something very close to this.